Hello everyone. I've had some time to check more details on the purple spot welder here, and I see that there is another improvement to be made with a simple mod, and that's related to the off time of the FETs. And yeah, this is all related to the fact that we are using here on this version, as many others, a simple optocoupler to drive all the gates. Now the on time is acceptable, but the off time is a little bit too long. It's if you see here, it's nearly 2 milliseconds. And that's not good because it takes some time for the FETs to switch off, and if you have a double pulse with probably 2-3 milliseconds delay, which is what is suggested, as you can see, it can be interfering with the off and on time, and so practically the FETs don't really turn off completely, and while the second pulse arrives, it's actually still on, so you have a overlap, which is not so good. And additionally, the FETs should be turning off quickly to be, on the safe side. So I would suggest to modify the resistor, which is a pull-down resistor on the gate. I will show this here. Okay, first of all, I will show you a better shot. Okay. Which is what I'm showing there. As you can see, this is a double pulse. I put a millisecond pulse as first pulse and 2 milliseconds as a second, just for demonstration purposes, with a delay of 2 milliseconds. If you look here, the delay is precise, so the electronics, the timing is sound, but the off time is nearly 2 milliseconds completely. Now, to reach the proper off, you should be going under Miller plateau and should be going under 2 volts, so that would be around here. But still, that's not really proper. So checking on other, let's see, I will show a couple of pictures here. Okay, let's go here and here. Okay, this is the on time. The on time is about 10 microseconds, which is fine for this purpose. Let me pull this in a little bit. Okay, this is from the datasheet of that FET. And as you can see here, the gate charge here, the Miller plateau, it appears around 4 volts, and that is exactly what's happening here. Here, time division, the voltage division is 2 volts per block, and as you can see, at around 4 volts, you start getting the Miller slope, the Miller plateau, and then it shoots up. Now, it's normal that it's not really flat because this is theoretical and this is the practical graph, so it's normal. And after around let's say 5-6 microseconds, it finishes, and that's when you have your on time here. So from this point onwards, the FET is fully the gate charge is fully saturated, and the FET is considered to be on, and the rest here is like slopes off and reaches the battery voltage. So this is the on time, and that's okay on this design. The problem is the off time. So let's go and get the off time here. For those of you who maybe see this for the first time, I suggest you check out my other videos, especially the frequently asked questions video in the playlist, where I explain exactly what all this means and why it's important, and the fact that this is a 6/12 FET, let's say, board. This is very important because every time you parallel a FET without taking into consideration the charge, you may have problems, because gates have a capacitance, and the more FETs you put in parallel, the more parallel capacitances. So you get a harder slope to charge, a harder gate charge to overcome,
and that little optocoupler really isn't designed for it. But that's another story, and I explained it in other videos. Let's see here now. I will go and show you exactly the off time. Let's see. Okay. See if I can find it here. Okay, so you can see this 500 microseconds. This is 1 millisecond, 1.5, nearly 2 milliseconds for this off slope, and that's a lot. This is how it's original. Now, the gate mod, somewhere here. Okay. Okay, so this is the original photo on time. Okay, this is what happens when you, let's say, put a 1 millisecond delay between the first pulse and the second pulse. You see that the gate charge has not depleted yet, and it's turned back on. That means that if this is above the Miller plateau, the gate is still on. That's not really nice to stay around the on area and then turn back on, because it means that the gate is not really off. So you're not really having two pulses, you're practically having one pulse, and you are overheating the FET, and this can lead to failures. Of course, usually you would put at least 2 milliseconds between the first and the second pulse, 3 based on what you're welding, so this effect wouldn't be critical in this situation. However, this is what happens. This is just an example which I did on purpose. And here is after the mod. This is the off time between the first and the second pulse. As you can see, it's been drastically reduced. It's about 248 microseconds respect to 1.8 milliseconds. Considering the fact that the Miller effect is around this area here, it's 150 microseconds, if not less, the off time. So it's much, the gates are much happier turning off quickly. That means that they heat up much less. So most of the heat generated by the FETs in this case are not actually due to the pulse current itself when it's on. It's actually the transitioning phase, because in this area here they're very subject to being delicate and having an internal higher resistance. Remember that the resistance of the drain source, the RDS, it's called RDS on, that's measured when it's fully on, it's fully charged. Gates are fully charged and gates saturated. In other areas of the gate state, then that's the RDS on milliohms is undefined, and you shouldn't be in that area. And that's usually what is overheating these FETs. So keep that in mind. A quicker off time is always better than a longer one. And let's see if I can find another. Yeah, this is another shot. Consistent, nothing changed. And okay, this is a double pulse with let's say the off time extended to 0. That says around 400 microseconds. Consider that this scope that I'm testing, so this is Zoe one that is being heavily publicized. I was curious and wanted to test it too. It has some rather strange measurement quirks, because it shows you 400 microseconds between this and this, while the time division is it's like slightly incorrect, but okay, that's another argument. Anyhow, it's much brief, much more short, and it's better, so you don't have the problem of turning it completely, let's say, off, or rather not turning it completely off. If you reduce this double pulse to 1 microsecond, you will see that it's off before the second pulse shoots in. And here are some other shots. So the mod, which I suggest you do, here it is. Let's see if I can show it Okay. Okay, this is the mod that I did. I used an SMD component and I replaced this resistor here. If you check, this is the output of the gate where I'm testing, when I'm probing with my scope. It goes through this 10 ohm resistor, and this is connected to the gate pin here. All these gate pins here, pin 1 on each FET, are in parallel. What happens is that this resistor here, the end of this resistor, is connected to this side. There's a bridge here. And this then goes to ground. This via here connects it to ground. So this is a pull down resistor. It's to turn the FET off. They put a 4.7K. It's pretty high, and that takes a while to, deplete the charge of all these gates in parallel, especially if you add more. So, it doubles the time. So if you have like 12 of them, you'll probably be seeing at least 4 milliseconds off time, which is an enormous amount of time for FETs. Let's see if I can find the original value somewhere. Not here. This is a modified one. Okay, this is my first test. This is a 1K resistor. This is the original value. If you check it out, it's 472, meaning it's a 4.7K. In parallel, this is ground. It was easier to then solder it here so you can see. In parallel, I'll put a 1K. So the total resistance here is actually less than 1K. But testing it by removing it and just putting 1K, I saw that, it's acceptable. You can keep 1K, it's fine. The difference is very little between the off time. Of course, this was a little bit shorter, but we're talking about, I don't know, 10 or 20 microseconds. So it's really, you can leave it with a 1K. If you can find an SMD component, 1K resistor, I took it off another board. You can simply remove this one if you're able to and just solder it in place of it. If you don't, you can use one regular resistor. This is a quarter watt resistor, and you can solder it without removing this one. It's fine. You can leave this one on in order to avoid, maybe creating other problems. The only thing you have to do is solder one end to this side of the resistors here. These two sides are in parallel, so you can solder it on this end or on this end. Or alternatively, you can solder it directly to any pin 1 of any gate you find, let's say, easier, handier for you. It's not necessary that you solder it exactly on this pad. If you find it easier, you can, for example, solder it here. It's hidden behind pin 1. You can solder it on this pin here, right, on this side. Be careful not to bridge pin 1 and the other and the source pins, because then nothing will work. So you can solder it on pin 1, and the other side you can solder it to ground. This side is ground, where this bus bar here, this is ground. Do not solder it to the other side. So you can solder it here between this pin and maybe this contact here. So that's the easiest way I can let's say suggest to do this mod. You could theoretically solder it on this side between this pin 1 here and the pad here, ground, if you have nothing here. It's up to you. Just be careful not to bridge pin 1 and the rest of the pins. These have to stay free. Check it with the tester. Pin 1 and the source pins here should not be shorted. These drain and source here should be independent from pin 1. Otherwise, if you short this with pin 1, nothing really burns out. It's just that the spot welder won't work. It won't trigger because this will be tied to ground all the time. So it's not a fatal, let's say, error, but yeah, it will, let's say, not be good for the optocoupler, which is pulsing something through a 10 ohm resistor to ground. It's not really designed to do that, but okay, it won't break immediately. Just be careful not to bridge pin 1 with the adjacent pins. So you can just solder it on this side here to any pin 1.
Easiest would be probably this side to this side, isolating the leg. If instead you are more handy with a soldering iron, do what I did. I just remove the 4.7 SMD resistor here and replace it with a 1K. I understand this is not maybe easy for many people, so the alternative is I showed it like this in this ugly way just to show where the wire goes. This side on here and the other side on ground. So you can do the same. Either you solder it here or you solder it to pin 1. Just don't bridge them and isolate cut them short and isolate them as you wish. Another thing I wanted to point out, which I forgot, not super important, but it's worth mentioning from the design point of engineering point of view, is that this mod, the decoupling mod, this wire here, decoupling capacitor should always be placed very close to the component they need to decouple. So the mod that's being shown here is an easy mod. It works, but it's not, let's say, the super proper way to do it, because this wire, which should be a good quality wire, by the way, multi-strand copper, least resistance possible, do not use any super thin wire. So I failed to mention that in the previous video. It's important that you use good copper grade wire here, because the current peak that can go through this wire coming from this capacitor initially can be pretty high. So any cheap wire or whatever, maybe fake copper or aluminum wire, you will be losing some voltage and current here, and it won't be really decoupling it properly. It does, but it's not going to be as effective. The mod with the previous version, which I did, where I placed the decoupling capacitor very close to it, is actually the proper way. I did this way for ease of use. Just keep in mind that if somebody were to point out, hey, but that's not how you decouple something, is completely right. You need to decouple with capacitors which are close to the component they need to decouple. Hence, this is the regulator. Here you have the smoothing capacitors which are close to the output of the regulator, and this is close to the input of the regulator. So that's how it works. For ease of use, as this is just, let's say, to compensate for any dip in voltage, okay, I guess you can keep it this way. Just keep in mind that this is effective, and I can show you this with some pictures of scope shots. Let's see, maybe you don't see it here a lot. Let me see if I can find a scope shot which is more significant to show you the voltage drop. Oh, maybe this one. Okay, so you see it starts here, and after like 2, 4, 6, 8, 10, 12, 14, 16, 18 milliseconds, you've lost like about 1.8 volts, because this is a 2 volt division, so it's loose. It's maybe slightly less, about 1.8, 1.6 volts. And that's the drop in the capacitor. Okay, so the capacitor, it's fine. I mean, you're still like 2, 4, 6, 8, 9, nearly over 9 volts, so the gates are on. It's not a problem. But as you see, the gates do lose, the capacitor does lose its power, its voltage, because it's also powering the circuit, the MCU, the microprocessor, and everything else. If you have 2 decoupling capacitors, you're only powering the gates with 1, and so it's a little bit, better. It's still fine. Keep in mind that this slope is linear, so the further you go down in time, let's say if you go to 40 milliseconds, you will be losing another 2 volts. So you reach 40 milliseconds, and from 9 volts you would be around 7. It's still fine. I mean, if you really are pushing your FET for 40 milliseconds, there are issues. So you have some battery issues, that's for sure. You weld with this welder properly 0.12, 0.15, I've tried 0.18 with double pulsed first, let's say around, I think I used 3 millisecond pulse as first pulse and 10 or 12 millisecond as second pulse with a 2 millisecond gap.
2, 4, 6, 8, 10, 12, 14, 16, 18. Yeah, this I was doing some tests here on I think it was 0.15 or 0.18 in wells. As you can see, the voltage is fine. It's not a problem, and the slope is, I mean, the voltage is still pretty in the safe side, on the safe side. Let's see if I can find something else. Oh, these are the off times that I was calculating. Miller, I've shown you this. This is after the mod. Here you see it's reduced to 200, around 240 milliseconds, because you know the off time is around here, so that's fine. This is with the 1K resistor pull down on the gate. Here you can see the difference between, here's when you have the two resistors in parallel, so that is the 1K in parallel with the 4.7K, which is originally on the board, and this is the other one. You can see that there is a slight difference between them. You see that this slope is slightly less steep than this one. That's just a slight difference in the resistance between the pull down. These are just a 1K, and here is a 1K with a 4.7K in parallel. It's very slight difference. You can keep the 1K. You can see it's not a real big deal. So yeah, this is the off time with just the 1K. Okay, this we've seen. Off slope, I think we've done them all. They're not in chronological order, so this scope saves them with random numbers. Every time you save them, the number changes, so I need to kind of like properly number them. Okay, this was the original one. Anyhow, the point was just to keep the gate off time short. So place in parallel here this resistor. You can choose a 1K, even a 1.2K, around that area, that value, if you want to place it in parallel. If you want to replace it, you can go ahead and place a 1K, and just be sure to solder one in here, the other one to the ground. You don't need to remove this. Just be sure, you know, to take care of what you're soldering. Don't bridge anything. This is with 6 FETs. I did not put additional 6 FETs, so I don't really see the point for my applications or in general placing all these gates in parallel without a proper driver. Now, there are people who've asked me to show how to actually modify the circuit, replacing the optocoupler and placing a proper MC, let's say, FET driver. And let's see, I think I might have, I think I saved somewhere a just give me a second. Oh, I placed it somewhere over here. It's an H bridge, but that's not the driver circuit. Let's see. Okay, I got this somewhere off the web. Okay, here, this is the optocoupler. Let's say this is coming from the MCU. It's driving the LED, the LED, the infrared LED in the optocoupler, okay. And the output goes to, there's actually a junction here. It's actually a very strange component, because here you should have a collector emitter style representation. The base is actually turned on by the infrared, so you don't have it. And this in turn is not connected to a FET. As you can see, it's connected to this MCP 1407 driver. And this then in turns inside has push-pull FETs. It's actually embedded in the IC. And you have the 2 half bridges, which are separate, and they're joined usually together by design on pin 6 and pin 7, and this drives the FET gate. Now this is, if you want to do this mod, you can either replace the optocoupler and put a FET driver
in place of it, or keep the optocoupler and route the output of the optocoupler to the input of the MCP and then the output of the MCP to the FET. It can be a little bit messy because you know, the board here there's not a lot of space, so probably can unsolder this and somehow put on a smaller board the MCP. If you can find the through-hole pin version, and you can find the SMD version, depending on what you're more comfortable in, like soldering. You could just remove this and use a SMD version and place it here somehow with a I don't know, some tape or even hot glue. Just wire the circuit and pin out properly, and probably need to add some. Here you have like some, this is a pull down resistor, you see, on the output, which is actually there, you know, so you already have this. And if you remove the optocoupler, you have the MCU output, which you can put straight to the input, and this is TTL compatible, so it's not a problem. You can put it in here. The fact that they keep the optocoupler is because it separates galvanically the driver from the MCU. So if something goes fatally wrong here, you don't destroy your MCU. That's the reason why you have this isolate this optocoupler here. In this case here, I guess that if you destroy something and it goes fatally wrong, you can probably throw the board for what it costs. But in a, let's say in an engineering design where you have, I don't know, like UPSs or switching power supplies where things are more expensive, well, you want to protect your stuff, so you're going to add protections and galvanically and optically isolating components to keep everything more isolated possible. So maybe I might be doing you know, a tutorial on this. It really depends on how much spare time. Unfortunately, I don't have a lot, as you've seen. I don't really post often, and I'm trying to, let's say, give you the best feedback I can on what I can see. I've been asked to check also some other spot welders, but you know, I buy this stuff by myself, and I try, as I said, with my spare time. So I don't really have the possibility to see them all. I have a collection of spot welders here, which it's like using paperweights. I don't really do a lot with them. I just usually use either one or the other. I was also wanted to do a follow-up for the Electrics with some further tests. I never really got around doing it because I had a lot of work. Anyhow, I hope this is helpful for you if you want to do this mod. Really, it's not difficult. You can wire it up as I've shown you here with a simple external resistor. If I can find the picture again, here it is. Just to show you where you have to wire it. As I said, you don't need to exactly wire it here. You can wire it on any pin 1. This is just a pull down resistor. It's to turn the gate off, to discharge the capacitance in the gate. It's like as if you have a capacitor here, you want to turn it off. This is not a push-pull. It simply removes the plus voltage from the gate, and the gate has to self-discharge through this resistor. It's totally a design flaw, but in this application it can be acceptable. Just the off time is not fast enough, so it's important that these FETs go off. If you have a proper FET driver here, it pushes it up, but it also pushes it down. That's why it's called push-pull, and so you wouldn't be needing such an arrangement, because the output of the driver, of the FET driver, literally pulls it down to ground. That's why it's very fast turning on, fast turning off. It's under the microsecond range. So it's extremely fast. And you might say, oh, you don't need this kind of speed for a welder. You're right, you don't. But the fact that you're turning it off and on very quickly, these FETs will be on their RDS. This means the milliohm designed internal resistance immediately, meaning that they won't be heating up as much as you think. Because if you do these mods, you will see that if you do a series of 20 pulses, the bore barely gets warm. Your electrode will probably get hotter.
These, however, won't be getting so hot anymore. Try it and you'll see for yourself that there is a visible difference. Of course, if you do 3 or 4 welds and then wait 5 minutes, you'll never realize. If you do several welds, one after the other, you will see a temperature difference, especially on the NTC here. This board has a temperature sensor, okay? It's actually placed here, close to the this side of the board. We should have placed it probably on the back in the middle where it's heating up, but they placed it on this side. So, okay, just keep in mind that it's around this place. And this reports a temperature back to the MCU. And you can keep an eye on it. So that's a good thing. Unfortunately, usually the temperature sensors are placed in the middle of the FETs, around here, usually either in line or on the back, or on the base, near the heat area. That's completely to the side area, so yeah, probably they're a few degrees off under. Okay, anyhow, video is long enough. In the meantime, if you haven't already, please subscribe, as that helps the channel. If you want to offer me a beer, that's always welcome. There's my email in the channel description. You can use PayPal, I think, yeah. And yeah, some people suggested opening a Patreon account, but I'm not really doing so many videos, so I don't know. Maybe, I mean, I'm talking just about spot welders in this case, but I'm actually you know, do a lot about different things in electronics, different things like you know, power supplies or retro computers. But there are so many channels already about that. It's you know, the YouTube area is full of these, so I don't know if it can be interesting or not. Maybe not. I might do some other arguments which can be interesting, or maybe some missing points. I don't know, we'll see. And anyhow, I hope you enjoyed this one, and hope it's helped. If you have additional questions, as usually, put it down in the comments. If you like it, like. If not, whatever. Just have a good weekend. And yeah, it's Sunday today for me, so yeah, end of weekend. And we'll see you next video if I have some updates, or if I find some other improvement. I try to keep them easy so that, you know, it's open to a bigger audience, which is what my initial goal was, not to complicate things too much for the let's say the average Joe. So, you know, adding a resistor here is easy. If you start going into too much into the details, SMD things, then can be complicated for many people, and maybe they can try, or, you know, usually end up with what I've seen is a not working board. So to keep things simple is always the best. Maybe it's not the best way, but at least it's better than keeping it default or stock, which, as I've always said, these things are kind of designed to fail, because in the end that's what they do. So anyhow, bye bye, and yeah, as always, see you next time.